Okay, great. Well, thank you so much for having me. I'm excited to chat a little bit about the work we're doing here at Aurelia. Um, for those of you who are not familiar, Aurelia Institute is a nonprofit space architecture R&D lab, and we also do education and outreach through chartering zero gravity flights and offering coursework on how to actually design for the microgravity environment and take people through designing and running their own experiments in zero G. And we also serve as a policy consortium. But today I'll be talking mainly about our R&D work and specifically about our self-assembling technology, um, which ideally, obviously, we sit in the land of human spaceflight, and I know this is mainly a robotics workshop. And so I'll be trying to keep a lot of the lessons broadly applicable to all sorts of space missions. But just wanted to kind of give you that background that that's kind of the angle we're approaching this, even if our system is adaptive and modular and robotic. That's kind of our end goal application. So quickly about me, just so you know where I'm coming from in kind of some of this conversation. So my own background was that I did my undergraduate work in aeroastro at MIT before heading to CU Boulder for my graduate work, where I did a PhD in bioastronautics, but I specifically looked at autonomous systems for use in deep space as part of the NASA Home project. Um, do you want me to pause? I'm not sure if the camera is working. You're good? Okay, thumbs up. Awesome. Um, and so along the way, I've interned a couple places. I worked at NASA JPL, on Juno, ironically, and also on the formulation side, as well as doing New Glenn GNC at Blue Origin, and now I'm the VP of Engineering at Aurelia. So on to the main focus of the talk. So today I'll be talking a little bit about TESSERAE. And so TESSERAE is a paradigm for self-assembly. It's a pretty brutal backronym, so apologies, it's a mouthful. But TESSERAE stands for Tessellated Electromagnetic Space Structures for the Exploration of Reconfigurable Adaptive Environments. And so this actually came out of our founder and CEO, Ariel Ekbla's PhD thesis, where she wanted to figure out a way to build large structures in space more easily. And so Tesserae's main feature is that it uses electropermanent magnets and state-based control to basically enable autonomous in-space construction. That's basically use case agnostic. Um, and so, like I mentioned, while we love the habitat use case, it doesn't need to be a closed form. It doesn't need to be a habitat. Tesserae can be used to build anything. It doesn't even need to be hexagons and pentagons. That's just kind of what we chose for the habitat use case to maximize internal volume to surface area. Um, and so we have some work happening in kind of a spin-out for-profit company right now, and they're looking into other things as well. But it could be used from anything from space-based solar arrays to parabolic reflector mirrors to radiators or asset shielding. But basically anything that doesn't fit into a conventional rocket fairing. So that's the goal with Tesserae. To give you a bit of an overview of the concept of operations, so in what we've baselined as our vision for Tesserae, it consists of 32 tiles to form that buckyball shape. So that's 20 hexagons and 12 pentagons. And the key aspect here is that it's launched in an unconfigured stack. So we like to joke that it's like Legos in space or IKEA furniture. And so in order to build out a volume that's wider in diameter than a fairing, we stack the hexagons and pentagons in the fairing and then deploy them and allow them to self-assemble utilizing the microgravity environment. Um, we call the assembly quasi-stochastic. And so another key feature of Tesserae right now is that there's no active propulsion. And so it really is just the sensors on board and the electropermanent magnets being throttled to allow them to self-assemble slowly using just that magnetic force on the order of hours, which is a slow process, but again, does not require a robotic arm, does not require EVA. And so right now we're proving out these dynamics and the adaptive sort of controls of that electropermanent magnet system to enable them to come together and assemble in space. I mentioned a lot of this, but the key components here are the EPMs, electropermanent magnets that I mentioned. There's two to a side. We initially did some trades on whether that was the optimum. Basically, it's kind of a weighing of complexity and additional mass for not a lot of performance benefit when we looked at 3 or 4 magnets per side, and found that one was just kind of not enough to enable the bonding we wanted. Um, Internally, we also have IMUs on board, magnetometers, a camera, which is new to Gen 5, and I'll talk a little bit more about Gen 5 in a later slide. And then the tiles use a state machine, which I'm unfortunately not allowed to talk about the details of, but it relies on Bluetooth communication for the tiles to chatter and be able to figure out kind of what's going on and when their bonding events are occurring. So this is an internal image of the Gen 4 tiles. So just want to point out some of the key features here. There is a daughter board that's also here, but the main image here on the kind of the base of the tiles is the controller board and the sensor boards that sit on each face, as well as the EPMs that are two to a side. Um, there's one pentagon and one hexagon. So these are the Gen 4 tiles, which were, I guess, like hand sized. Right now, the Gen 5 tiles are a little bit bigger in size because of the camera addition. And I'll chat kind of about some of the trade-offs there as well. So Tesserae has been flying for quite a few years, just from our founder's thesis through the founding of the nonprofit and this current ISS flight we're working towards. Um, One of our kind of key aspects of, this is not new for anyone in aerospace, but really trying to test incrementally. And so our first generations were tested on zero gravity flights. So for those of you who are unfamiliar, it's kind of affectionately called the Vomit Comet, and it's an aircraft that pitches up to 45 degrees before pitching over for another negative 45 degrees to give you about 20 seconds of weightlessness. And so the first generation of tiles was really tested initially on those zero G flight, and we have continued to use zero G flights to test out additional changes in the hardware and in the software to make sure that we're testing out things like bad bond diagnosis and recovery, some of the faults that we've noticed before spending money and a lot of our effort towards these bigger launches or flights. 20 seconds is not a lot of time, but fortunately, we usually do 30 to 40 parabolas, which is great from a data point perspective. It's less great from like a stomach and nausea perspective. But we are able to do just a lot of our initial checkouts during those flights. Later generations, so second gen is when the tiles really started to kind of look more like the current generation. Those were tested suborbitally on a Blue Origin New Shepard flight. And then the third and fourth gen were tested on the ISS in what we called a floret configuration. And so that was not the whole buckyball, it was just a single pentagon and 5 hexagons that were released by hand by an astronaut and allowed to assemble in microgravity. So the fifth gen here, you can see them sitting in the dispensers. That's also a new kind of feature for this flight. They're sleeping, they're charging in their little bookshelves before launch. And so just want to talk a little bit about the differences. So we have flown twice to orbit before. This is the floret of the Gen 3 tiles floating on ISS in front of the cupola. And we'll be flying back to ISS with the full buckyball. So that means all 32 tiles will fly with 2 spares. Unfortunately, we will not be getting the cupola for this assembly. We are basically being relegated to an aisleway where we have found enough space and we're able to kind of carve out an area that wouldn't get too much in the way of the astronaut operations. Um, and we're doing a week-long demonstration, which gives us about 5 days of repeated assembly, and also kind of on the ground. Meanwhile, we'll be able to review data each day and then basically do live ops and able to kind of push any software updates we need to during the operations. Some of the key upgrades here, so machine vision, that's the big one. We wanted to give the tiles intelligence of basically identification of who they're bonding to and which face of that tile they're bonding to. To start to kind of get like a global intelligence of the structure as it came together. Um, this is also pretty useful in helping us diagnose some of our bad bonds, which I can talk a little bit about, but sometimes the tiles, when they come together, don't gracefully come together with the magnets fully aligned. They'll come together a little bit off kilter and be attached but not fully secure. And so that was some early behavior that we noticed. And then basically baked in the intelligence with the magnetometer and with other sensors for the tiles to now recognize when that happens and to reject the bond, in which case the capacitor fires, electricity then, flows through the electropermanent magnets and then turns off effectively, basically counters magnetic field, and allows the tiles to separate and try again. Usually this results in a full recovery and in a full good bond. Um, I think I mentioned this, but the dispenser is new. So previously tiles were handheld and then hand released. We wanted to more closely mimic what a real life mission would look like, where the tiles would be coming out of a fairing, kind of like a Starlink mission, and have a dispenser. And so we've built out that stack and are currently using it sort of as like a communications hub for a lot of the Bluetooth and some of the command and data handling that's coming down. Finally, we're also building out a containment system, primarily because NASA does not want the tiles, uh, the risk of the tiles like floating down the aisleway. So we had to partition off our experiment corner just to make sure that they would not get lost. So here's some process images. On the left here, we have the tiles, just the bottom half of the tiles and electropermanent magnets being epoxied in. Um, like I said before, the earlier generations could fit in the palm of your hand, and these are quite a bit bigger. And so you can see a laptop in the back there for scale. And then here's the dispensers and the tiles at NASA for testing earlier this month. We're getting them back hopefully in about 2 weeks, where we'll do some final adjustments before getting them ready for hardware handover. Here's our electrical engineer, Jamie, working on them. Um, and here's a good picture of the tiles and kind of their actual size. So we joke that they're like roughly dinner plate size now. And when fully assembled, the buckyball will kind of be like a small or medium-sized beach ball. So definitely not a small object anymore, which is kind of fun to see. I can definitely chat a little bit more about this if needed, but one notable feature here that's kind of vestibular or not really, or vestibular, yeah, not really being used at all, is the solar panel. And so one thing we wanted to test out initially with this generation was to add the ability for the tiles to recharge in flight, much like we'd envisioned them for a full extravehicular assembly. However, we quickly discovered that synthetic light or LEDs is not the sun, and so the solar panels that we acquired did not basically charge in the same overhead task lighting that the ISS has. So they are now kind of a moot point, and they're still on the Gen 5 tiles. They're not going to work. They're okay in the actual sun. They're not great for indoor charging. So the tiles do charge by getting plugged in the back, just by contact, which makes it easier for the astronauts to load them up for the next run. But unfortunately is not the best kind of test of the forward architecture we wanted to deploy. And finally, I know a lot of you here are more interested in fully robotic exploration and interplanetary exploration and less about the sort of humans, but I wanted to kind of talk through some of our lessons learned through our development of the TESSERAE system. This is kind of an obvious one, but minimize complexity. There's a reason we chose not to add active propulsion and not to use a robotic arm. Uh, we are really trying to see what kind of how little we can get away with, basically, to make this sort of as least as simple as possible while still enabling autonomous assembly. Number two is the importance of graduate interns. So the April tags that I mentioned, which are effectively like a low fidelity QR code, came to us via our graduate intern from Princeton last summer, Sneha. She's awesome. And so I firmly believe in having a great intern program, but also in using the interns as a way to kind of get new ideas into the mix. Especially if they're coming from a graduate program, they're often closer to some of the state of the art or kind of novel systems that are coming up and might know some scrappy ways to do things. Procure early. We live in kind of times where we've been burned by a couple procurement issues, and so making sure that you're on top of things you might need down the line, get extras. That's been something that we've had to learn for sure. And finally, test incrementally, test creatively, and test everything. So this is not new to aerospace by any means, but testing is expensive. We don't go to the ISS every year. We don't get to fly every single new feature, even on a zero-G flight. And so we've had to get pretty creative with how we do some of our testing. We'll do string tests. We'll do basically air hockey table tests where we put the tiles on a simulated flat floor and have them at least move in 2 dimensions and be able to test out certain dynamics that way. We also just do kind of dorky hand tests. So we'll force bad bonds. We'll force them to clump, which is when they basically start to attract each other back to back, and then allow them to at least be able to detect that and train what thresholds we need to be able to have to recognize when those bonds are occurring and then to reject them. Um, so yeah, that's a really quick overview of the TESSERAE system and some of the work we're doing. But looking forward to any questions. You guys can feel free to reach out to us at Aurelia or to me personally afterwards. But yeah, I just want to say thank you so much and looking forward to any questions.
Okay, thank you, Annika. Let's hold off the questions for the panel.